In this video, I'm going to be talking about quantum numbers. So quantum numbers, for the sake of this class, you can think of them as increasingly specific coordinates for locating an electron in an atom. There are 4 different types of quantum numbers, and every single electron has a set of 4 quantum numbers. And when you put the 4 of them together, that tells you the exact location of that electron within an atom. Okay. Now, I'm going to set up a little bit table. So quantum number. Name. I'm going to say what it defines. And then possible values. Okay, so the first quantum number is represented by the letter n, and this is what I alluded to last video at the end when I was talking about the Rydberg equation. This is your n. It's called the principal quantum number, and it tells you what shell, what energy level you're in. So it defines the size of the shell. Size of shell. And when I say shell, so if I have nucleus here, this right here, so here, I'm going to shade it here in blue. That's your first energy shell. And I'm going to say in green here, that's your second energy shell. And if I had drawn more shells, so on. So basically just what energy level it's in. That is what's defined by n, the principal quantum number. And n could be any integer. It just starts at 1. So again, this first one is 1, then 2, 3, and so on. Okay. The second quantum number is represented by the letter L. And this is referred to as the azimuthal quantum number. Now, this one, I think in my opinion, because azimuthal is a bit of an unusual word, I've seen different names and different terms used for this quantum number. So it's possible that you may, if you're studying online or something, you may see different terms. But the official term is that it's the azimuthal quantum number, and it defines the shape of the subshell. So what does that mean? Within each of these shells, there are different subshells, and different subshells have different shapes. So let me finish this chart. So the possible values, it can be 0 is the lowest value, and then from that it goes to every whole number all the way up to n minus 1. So what does that mean? Well, let's say our n value is 3. If our n value is 3, then n minus 1, 3 minus 1 is 2. So that means that L could be 0, 1, or 2, but that's it, right? It can't go beyond 1 less than whatever the n value is for that electron. Now, these have specific letters that are associated with those numbers. So I'm going to make a chart down here. So the L value. So if the L value is 0, 1, 2, or 3, and I'm going to say the letter designation. So if you have an L value of 0, and again, this will make more sense in my next 2 videos as well, but if you have an L value of 0, that's represented by the letter S. An L value of 1 is represented by the letter P. An L value of 2 is represented by the letter D. And an L value of 3 is represented by the letter F. Again, in my next video, I'll explain a little bit more what that means. But just know that if you see these letter designations, those correspond to these respective L values. Okay. The third quantum number is m sub L. Oh, I apologize. I do also want to talk a little bit about shape. So what I mean, so an S subshell is just a sphere. So I'll draw it as a circle since it's two-dimensional. But a P subshell is actually, its technical term is it's a dumbbell shape. It actually looks like this. So you have several of them, and they could be have different orientations. But that's actually, so let's say we have, this is our n equals 1 energy level. Within it, you have this larger sphere. I'm going to try to draw it lightly. Just shade it in lightly. So that is your n energy level. But at the same time, overlapping that, you also have some p. Sorry, not energy level, subshells. Right. And there's a reason I drew 3 of them, but we'll get to that with the next quantum number. So basically, you have different subshells overlapping each other within the larger energy level, or the larger shell. So this is what I mean by each quantum number starts to get increasingly more specific about exactly where the electron is. So the first one tells us what energy level that electron is located in. The second one tells us which subshell within that energy level it's located in. So now the third one is m sub L, the third quantum number. That's referred to as the magnetic quantum number. And that tells us the orientation of the orbital. So I'm going to take, so m sub L can have a value from negative L at its lowest all the way up to positive L. So for instance, let's say if L is 1, which again corresponds to P, the dumbbell shapes. If L is 1, then m sub L, so I guess if L equals 1, m sub L can equal negative 1, which is the negative L here, then go up just a whole number each time, 0, or go up 1 each time, then 1, and it has to stop there, stop at positive L. So you have 3 different values for m sub L. Well again, if we're drawing these p orbitals, you can draw 1 vertically, 1 horizontally, and then 1 diagonally. And they all intersect each other. So basically this is 1 orbital, that's a second orbital, and that's a third orbital. So those are 3 different orbitals all within that subshell. And so basically each one of these values, negative 1, 0, and 1, correspond to one of these. It doesn't really matter which one is which, but one of these orbitals correspond to each one of those numbers. So, and you can see that the orientation of them is different. And once you get into D and F, they have far more complex shapes, so you don't have to worry about the shapes of D or F orbitals, but they also do have different shapes and different orientations as well. So, basically, the orbital within the subshell that the electron is located in tells you, you're told that by the m sub L quantum number. And lastly, our final quantum number is m sub S. And this is the spin quantum number. And what that tells you is the spin of the electron. So one thing, so this could either be plus 1/2 or minus 1/2. Basically what you need to know is that in each orbital, so again, each one of these is an orbital, every orbital can contain a maximum of 2 electrons. So and one of them we just say has a positive spin, the plus 1/2. One we say has a negative spin. So again, starting from the top, the first quantum number tells us the energy level, the shell that that electron is located in. Then the second quantum number tells us which subshell within that shell the electron is located in. The third quantum number tells us which orbital within that subshell the electron is located in. And then the final one tells us which of the two electrons in that orbital we're talking about. Okay? So, for instance, just expanding upon this a little bit more, let's say we have a principal quantum number of, let's go with 4. So n equals 4. If I were to ask you what all of the possible L values are, well, again, L can only start at 0, and it can go up to 1 less than n. So, in this case, L could be 0, 1, 2, or 3. Let's say if L is 2, so if we're going to 2, what could your M sub L be? Well, it can go from negative L, so it's starting at negative 2, and count up negative 1, 0, 1, 2, all the way up to just L, so negative L to L, and those are the possible 5 values you could have for M sub L if your L value is 2. And again, M sub S is always just plus 1/2 or minus 1/2. So another type of question you could have is you could be given a list of 4 quantum numbers, and say, is this a possible set of quantum numbers? So let's say n equals 3, L equals 2, M sub L equals 3, and M sub S equals plus 1/2. So if the question says, is this an allowed set of quantum numbers? Well, n equals 3, sure. N could be 3, that's fine. L is 2. Well, if n is 3, the lowest that, or L could only go up to 1 less than that, which happens to be 2. So, an L of 2 is perfectly acceptable when n is 3. M sub L of 3. Well, remember, the M sub L can only go as high as positive L, which means in this case, it could, if L was 2, it could only go up to 2. So an M sub L of 3 is not possible with L being 2. So this is not an acceptable set of quantum numbers.